Okay, so the matrix vector multiplication format, the MEM takes a vector of dimension n. So this we call as a vector of dimension n. This is a vector of dimension n. Okay, right? So this is my input signal, and this is my output spectrum. So the input signal and the output spectrum, which are discrete in nature, can be represented as n by 1 or n dimensional vectors. N dimensional vectors. Now, a vector representation of a signal is either a column matrix or a row matrix. A column matrix or a row matrix. So in this case, it's a column matrix. Small x is a column matrix. Capital X is a what? Capital X is a column matrix representing the spectrum. So what I will now do is I will just represent this in the standard form. That's in the matrix vector multiplication format, and then I'll use the whiteboard to illustrate this. Okay. I hope this screen is visible. Is this okay? Is this visible?
Yes, sir.
Yes, sir.
Okay, so what we have now is a input vector. So this is my input vector. I will represent this like this. X bar. So X bar refers to a column vector that consists of the samples of the input signal x of 0, x of 1, etc. up to x of n minus 1. So this is my input vector. So this I call as x bar. This is x bar, right? Now x bar is multiplied by a matrix W. This is the matrix of the complex exponentials Wn raised to nk. So this will give you the output vector x bar, capital X bar is equal to W into x bar. So this is an n dimensional vector. So that I represent as an n by 1 vector. This is an n dimensional vector. So this I represent as an n by 1 vector. And this is, pardon me, this is an n by n square matrix that relates the input vector to the output spectrum, right? So this is what we have discussed right now. Okay, so I'll go back to my presentation. Okay, so this is the matrix vector multiplication representation of the DFT computation. So likewise, I can also think of the matrix vector multiplication representation for the IDFT computation. So let me write that also. So I will do that also now, and then we'll go back to my further slides. Okay, so let's again share the whiteboard. Is the screen visible? I hope the screen is visible.
No, sir.
No, sir.
It's on? Okay. So
No.
what about now?
Yes, sir.
Okay. It's visible, right? Okay, thank you. So
Yes.
we will write the expression. We will write a similar expression for the. We will write a similar expression for the IDFT also. IDFT. So for the IDFT, it should relate x. Sorry. So it should relate x to a capital X. So you should have some W inverse, right? Is it clear? Why? Because you had capital X bar is equal to W into X bar, right? So this is your what you call as the analysis equation, and this should be your synthesis equation. Synthesis equation. So now, if I look at the expansions for the analysis and equation, synthesis equation, it's very evident that you should be able to write W inverse should be equal to 1 by n into W conjugate. Can you understand this? Can you see? Can you identify how we have written this? This is written by observing that you have this equation for the synthesis, that is x of n is equal to 1 by n. So you have that 1 by n here. So that should be this 1 by n. 1 by n sigma k equal to 0 to n minus 1 x of k w n raised to minus nk. So now observe that you have this wn raised to minus nk. What is wn raised to minus 1? That should be e raised to plus j2 by n, right? And that is the conjugate of e raised to minus j2 by n. So every element of the new matrix would be multiplied by a 1 by n, and you will have a conjugation of this side. You will have a conjugation of the complex exponential. So 1 by n into w conjugate. So w inverse should be equal to 1 by n into w conjugate. Is that clear?
Sir, can you repeat that point?
Is it Meenakshi? Meenakshi, right?
Yes,
Question
sir.
was from Meenakshi, right?
Yes,
Okay,
sir.
so you observe that the analysis equation, this is the analysis equation. Analysis equation is written as x bar is equal to w x bar, which is the analysis equation. X bar being the input signal, capital X bar being the output spectrum. Capital X bar is the output spectrum, right? Is that clear?
Yes, sir.
Okay, so there should be an inverse expression for that. So going back to x small x bar from capital X bar should be therefore the synthesis equation. So this should be the synthesis equation.
Okay, sir.
Okay. Okay, so now let us expand that synthesis equation. This is the expansion for the synthesis equation. In fact, this is the matrix vector multiplication equation for synthesis. This is the synthesis equation, and this is the MVM equation for the synthesis, right? Matrix vector multiplication equation for synthesis.
Yes, sir.
Okay, now let us look at this expression. So this would be 1 by n sigma k equal to 0 to n minus 1 x of k w raised to nk. So which I will now write here as sigma k equal to 0, k equal to 0 to n minus 1 x of k into w n raised to minus k by n. So I look at a matrix like this now. W raised to minus nk by n, which again I will write as sigma k equal to 0 to n minus 1 x of k into, I'll put this here, 1 by n wn raised to minus 1, sorry, 1 by n, one by wn raised to minus 1 whole raised to nk. Is it okay?
Okay, okay, sir.
Okay. Now, how will I write this as a matrix vector equation? This will be your input signal, right? This will be your input signal x. So that is appearing here. And the rest should represent W inverse. Is that clear?
W.
Okay.
Okay, sir.
So you have this
Yes,
1 by n here, and wn raised to minus 1 is the conjugate of wn. Wn raised to
Yes,
minus
sir.
1 is the conjugate of Wn. So which means every element in the matrix is now replaced by the conjugate. Every element of W should be replaced by the conjugate of that, and then every element should be divided by n. So W inverse should be equal to 1 by n into W star. Is it understood? Meenakshi, or do you want me to explain that further?
No, sir. I got.
Okay. Okay, so we will go back to the presentation here again. Okay, so we are back to this previous slide. Now you have matrix vector multiplication equations for the analysis as well as for the synthesis equation. Like that, every DSP equation can be represented in a matrix vector multiplication format. So you might be remembering the Toeplitz matrix structure that we had discussed in the previous semester. Toeplitz matrix structure, when we discussed linear convolution, do you remember? We had discussed linear convolution in the previous semester itself, and then we had tried to represent that linear convolution in the form of a matrix structure. If you do not remember, we will be doing that again today. So that matrix had a peculiar structure in the sense that it's all the diagonal elements are the same. Not only the leading diagonal, all the diagonals, all the leading and non-leading diagonals were the same. So we will formulate that once again today. Okay, anyhow, matrix vector multiplication formats can be used to represent any DSP operation. So whenever you find a matrix vector multiplication format, you have to understand that there are several simultaneous equations that you are referring to. In fact, matrices, you studied matrices to represent simultaneous equations. Okay, so just a second. I hope this is visible. Abhishek?
Yes.
Okay, right. So now we will move on to another representation. So these are only representations to compactly represent DSP operations. So this representation we will call as a modular representation, and we will see why this modular representation is significant. You might have heard about this word modulo operation. So modulo operation is just the computation of the remainder. When you compute the remainder for an integer division, so generally we refer to only integer divisions. It is not that modulo operations are not defined for non-integer operations, but they are actually defined, but we will be sticking only to the integer modulo operations. So in computing, you might have this modulo operator whenever you use a high-level language programming such as Python, or maybe when you use packages such as MATLAB or Scilab or Maple or Octave, etc. You will have this built-in modulo operator. So what it basically does is it will compute the remainder after a division of one number by another number. But it's slightly different from the conventional remainder that we see. We will see how it is done. So now, for example, modulo operator is referred to, it's represented as n modulo n. So n within two brackets and capital N as a subscript. So it refers to the remainder of n divided by capital N. So for example, what would be 5 modulo 2 in that case? What would be the remainder of 5 divided by 2?
1.
That would be 1. So that's it. So 5 modulo 2 would be equal to 1. And what would be 3 modulo 2? That's also equal to 1. And what is 1 modulo 2? That's also equal to 1. Now you can do the same when the dividend is a negative number. So we will see how this is done when the dividend is a negative number. So that is done slightly in a slightly different manner. Say for example, how you do compute minus 6 modulo 3. So we look at minus 6 modulo 3. Let us see how minus 6 modulo 3 is computed. Minus 6 modulo 3 is computed as you take the next integer multiple of 3. So that would make the result either 0, that would make the difference either 0 or positive. So next higher integer multiple would be 3 into 2. That is 6, and we will take the difference between 6 and the negative number minus 6. So 6 minus 6 is equal to 0. So here minus 6 modulo 3 is computed as 6 minus 6 modulo 3. And minus 3 modulo 3 is computed as 3 minus 3 modulo 3. So that's equal to 0. So the remainder is equal to 0. And minus 5 modulo 3 is 6 minus 5 modulo 3. So that is equal to 6 minus 5 modulo 3 would be equal to 1. 6 minus 5 modulo 3 is equal to 1. And minus 4 modulo 3 is 6 minus 4 modulo 3 is equal to 2, which is the same as that for minus 1 modulo 3, which is equal to 3 minus 1 modulo 3, which is equal to 2. So we will see why this is done. What is the significance of this? So I will switch on to the whiteboard and let us see why this is important in our representation of digital or discrete signals. So this will help in representing the index in a very compact manner. So this notation has to be perfectly understood, and we will finally see what will be x of n modulo n, what this actually represents. So now let us look at this modulo operation. We will illustrate the modulo operation, and then we will see why this is important. Okay, so let me draw a straight line here. Sorry. Oh, assume that this is a straight line. Okay, so this is 0, 1, 2, this is 3, this is 4, 5, 6. I will mark the negative values, minus 1, and we will continue up to minus 2, minus 3, minus 4. So I'll write a few more values. See why, to illustrate why this is important. Minus 5, minus 6, etc. And now we will write, so these are the values for n. So this is n. Now let us compute n modulo 3, and we will write the values underneath this. So what is 0 modulo 3? 0. 1 modulo 3 would be what? Please tell me. Remainder of 1 divided by 3 is? Anyone?
1, sir.
1. So otherwise I will understand that all of you are sleeping. So this would be 0, 1, 2 modulo 3 would be 2. What is 3 modulo 3?
0.
0. This is again 1. This is 2. This is 0, etc. So let us write what is minus 1 modulo 3. What is minus 1 modulo 3? That is 3 minus 1 modulo 3 is, please tell me what is that?
2, sir.
This is 2. So this should be 1. This is 0. This is again 2, 1, 0. So the indices occupy only 3 values, 0, 1, 2, 0, 1, 2, 0, 1, 2, etc. So these are the only unique values. The values are only from 0, 1, 2, which is 3 minus 1. So if I write n modulo n, it will have unique values only from what? Please tell me. 0, 1, 2, etc. up to n minus 1, right? Is that understood? So let me now think of a signal x of n. So x of n, let us say it has only 3 samples, and the samples are 1, 6, or 4. These are the values. So at 0 you have 1, at 1 you have 6, and at 2 you have, let's say, 4. So these are the samples. This is 1, 6, 4. So this is x of n. Now let us look at x of n modulo 3. What will be x of n modulo 3? So x of n modulo 3, for these values are 0, 1, 2, so these are the same. Now what is x of 3 modulo 3? 3 modulo 3 is same as 0. So x of 3 modulo 3 should be the same as x of 0, right? Is that okay? I hope you understand. X of 4 modulo 3 is same as x of 1, so this should be 6. And x of 5 modulo 3 should be 4. And here again, this should be 4. This should be 6. And this is 1. So this is 6, 4. Sorry, 1, 6, and 4. So again you have what? 4, 6, and 1. So you evidently x of n modulo 3 is a periodic signal. I hope you appreciate this. X of n modulo 3 is a periodic signal whose one period is the same as x of n. Is it clear? Is this clear?
Yes, sir.
Okay, so therefore you can write your x tilde of n, which is a periodic sequence obtained by periodically replicating x of n, as equal to x of n modulo n, right? So this is what we can conclude from here. Now this is why this modulo operator is significant for us. X tilde of n is x of n modulo n. X tilde of n is x of n modulo n. So this is very important for us. Now we will be using these modulo operators to represent our sequences very compactly. So again, let us go back to our presentation. Okay, so we have seen why this modulo operator is important. Now we will use these modulo operations to look at certain properties. We will compactly represent the DFT and look at certain properties of the DFT. So let us start with the first property of the discrete Fourier transforms. The first property of the discrete Fourier transforms, can you make a guess what will be the first property of the DFT? We are looking at a linear transform. DFT is a linear transform. Why do you say DFT is a linear transform? You had seen properties of DTFT, you had seen properties of Laplace transforms, you had seen properties of Z transforms. Every time you started with a property called as the linearity property, right? Linearity property, why do you say it? When do you say a system is linear?
When it's both additive and homogeneous.
when it is both additive and homogeneous, or in other words, it satisfies a property called some property that you had studied in network theory. You have studied that in network theory, I hope.
Superposition
It's
theorem.
superposition theorem. It's the superposition theorem. So when the transformation, if you can call the system as the transformation, or if the system does the transformation, if that system obeys superposition theorem, then you say that the transform is linear. So to put it into words, if you take the discrete Fourier transform of a sequence, and if you take the discrete Fourier transform of another sequence, then if you compute the linear combination of the discrete Fourier linear combination of the two sequences, say for example, you take the first sequence as x1n, take the second sequence as x2n, take a linear combination of x1n and x2n, then what does it say? Its discrete Fourier transform would be the similar linear combination of the individual, similar linear combination of the individual discrete Fourier transforms. So that is written here. So all the properties of the discrete Fourier transform are defined for 0 less than or equal to n, k less than or equal to n minus 1. So we will only look at one period. Now you have seen that this discrete Fourier transform is one cycle of the discrete Fourier series. So whenever you are required to prove the properties of the discrete Fourier transform, you only need to prove the property of the discrete Fourier series and then look at the property for one cycle. So that is how you prove the properties for discrete Fourier transform. Because DFT is one cycle of the DFS, so you look at the proof for the corresponding property in DFS and then look at one cycle for the property for the DFT. Now, if x1n has got an endpoint DFT, so actually that n should be written below that arrow. So it should be x of n, that double-sided arrow, you write DFT on top and write n at the bottom. So n point DFT, that will indicate n DFT, or you can even put n at the top and DFT at the bottom. Or because math typing in math type is very cumbersome. So that is why I put this as n DFT. So read this as n DFT. Now, Helena Saju, can you tell me what is this n DFT? This we have seen towards the end of the previous class.
Sir.
N DFT, why do you write this n DFT? Say for example, I will put a numerical value to n. Let me put this value of n as equal to 8. I will write 8 DFT. What does it mean?
Okay.
Currently, towards the end, we have discussed about zero padding, right? Do you remember that?
Yes.
So
yes,
this has
zero.
got something to do with zero padding. Okay, can you try to make a guess at least, even though I might not have explicitly said what is NDFT? Anyone in the class who can answer this?
Endpoint DFT.
10 point?
Alla sir, endpoint DFT. Like it doesn't make any change to the signal.
If you go on adding zeros towards the end, towards the end, it is not going to make any change to the structure or the properties of the signal. At the end, if you add zeros at the beginning, it's equal to delaying the signal. But if you add zeros at the end, you are not making any change to the signal.
Changes.
Say for example, if you had a signal having only 6 angles, if you had x of n having 6 angles, so that we can relate to a 6-point spectrum via a 6x6 DFT forward transformation matrix W, right? That we had seen. Is that clear? You can write this W6 raised to nk and let n and k vary from 0 to 5. So you have a matrix. So that matrix is a 6x6 matrix which relates the 6x1 x of n to the 6x1 x of k, capital X of k. So you have this 6x1 matrix. Is that clear? Now what is the spacing between the frequency samples? That also you have seen. What will be the spacing between the frequency samples? You have seen that k is equal to 2 pi by n, right? K is equal to 2 pi by n. So the spacing between the samples will be equal to 2 pi by 6 in this case. Number 6, 2 pi by 6, because there were 6 samples in x of n, and there are 6 samples in x of k. You have discretized the frequency spectrum by taking 6 samples in the frequency spectrum, which covers the range from 0 to 2 pi. So the spacing between the samples is 2 pi by 6. Understood? Is that clear? If you have any doubts, please ask. Am I audible to everyone? Hello?
Yes, sir.
Yes, sir.
I'm not very sure about my internet connection, but to me it seems to be okay, but I am not very sure. In between I had a message that it is unstable. I hope this is okay now. Was I audible throughout?
Yes, sir.
Yes, sir.
You are audible.
Okay, so now you have 6 samples in X of k. You are taking a 6-point DFT. So which means you have divided the frequency spectrum from 0 to 2 pi using 6 samples in the frequency spectrum. So remember that while you had gone from x of e power j omega to x of k, the substitution that you had made was you put, instead of evaluating continuously from 0 to 2 pi or from minus pi to plus pi, in our case you are looking at 0 to 2 pi. Instead of evaluating at all continuous values from 0 to 2 pi, which would be impossible, you are now evaluating only at discrete frequency points, which are given by k is equal to, which are given by e raised to j 2 pi by 6 into k, where k takes values 0, 1, 2, 3, 4, 5. Is that understood? So which means the spacing between two frequency samples will be therefore 2 pi by 6. 2 pi by 6. So if you have a 6-point input signal and if you have a 6-point spectrum, then the spacing between the frequency samples is 2 pi by 6. I will draw that and explain. Now if I put 2 zeros at the end, now the input signal is x of n followed by 2 zeros. So does it make any change to the information content of the signal? It does not. If I take the 8-point DFT of this sequence, then the spacing between the frequency samples is now 2 pi by 8. Earlier it was 2 pi by 6, now it is 2 pi by 8. So I will illustrate that by drawing a figure. So let us again go back to the whiteboard. Okay, so let us think of a signal x of n is equal to, I will put some numerical values instead of drawing this, so that will be easier. 1, 6, 4, 4, 6, 1. So how many samples are there? There are 6 samples. So if you use the analysis equation, you might get some x of k, where x of k consists of, I'm not going to compute this, so I will just write this as x of 0, x of 1, x of 2, etc. up to x of 5. Is it understood? There are 6 samples. So this takes the angles from 0 to 2 pi radian. So this is 0 radian. This is what? 2 pi by 6 radian. This is 2 into 2 pi by 6 radian. And finally, this is 2 pi by 6 radian into 5. Is that clear? So that the next sample is at the angle 2 pi by 6 radian into 6, which is the same as 0 radian. So you only have 6 samples. So this is one cycle of the periodic axial day. Okay. Now I put 2 zeros here. X of n is equal to 1, 6, 4, 4, 6, 1, 0, 0. So these two signals are the same, in fact, because you have not captured the last two samples. So you can very well assume that there are no samples here. So you can put zeros here. And now the new x of k would be having, what are the samples? X of 0, x of 1, etc. up to x of 7. Now the spacing between the samples would be 2 pi by 8 radians. Is this understood? So if I had some spectrum, so that's x of k would be the sampled version of the spectrum. So if that continuous spectrum, so this is, I'm going to draw x of e power j omega. So x of e power j omega, let this be a real signal. This is a real signal. So this is my x of e power j omega. I will mark this as pi by 2 pi radian, and this as 2 pi radian. So the unique range of frequencies is to be from 0 radian to 2 pi radian, or let's say this is from minus pi radian to plus pi radian. So this is the unique range of frequencies. So this is being sampled at 6 points. So I will use a different color to mark the samples. So maybe you have first sample here, second sample here, third sample here, fourth sample here, like this. This is how it is sampled. So 6 samples are taken, like this. Second sample here maybe, third sample here maybe, fourth sample, fifth sample, and the sixth sample. So maybe this is how you take the samples. So these are separated by 2 pi by 6 radian. So my figure is not actually very correct, because I should have positioned the lines in a more accurate manner, but you can very easily understand what is being tried to be portrayed. So the spacing between the lines in the frequency domain will be 2 pi by 6 radians. Whereas now if I look at a spacing of 2 pi by 8 radian, now this could be how the lines are spaced now. So you have 4 points here, 5th point here, 6th point here, 7th point here, 8th point here. So now you evaluate the spectrum but at different frequency points. Is that understood? Do you need further explanation for this? If I put 2 more zeros, does it change the information content of the signal?
No, sir.
Okay. If I put 2 more zeros, what will be the spacing in the frequency domain? It will be 2 pi by 8 radian. Earlier it was 2 pi by 6 radian. So now you are evaluating the continuous spectrum, continuous x of e power j omega at a new frequency sampling instances, which are separated by 2 pi by 8 radian. If there were no zeros, it would have been evaluated at samples that are separated by 2 pi by 6 radian. So now if you need any information regarding, say, so if you sometimes you might be required to estimate the frequency sample at 5 into 2 pi by 8 radian. So you might be required to estimate what is the frequency at 5 into 2 pi by 8 radian. So in that case, you should have a sample at 5 into 2 pi by 8 radian. So this is 0, 1, 2, 3, 4, 5. So here, this is the value. So unless you have a sample at this value, you will not be able to capture what is the value here. If this separation was only 2 pi by 6 radian, if the separation was 2 pi by 6 radian, then you would not have had a sample at 5 into 2 pi by 8 radian. So that is the advantage, that is the significance of zero padding. So we'll go back to our slide once again. And okay, so this is the linearity property. So x1n has got an endpoint DFT given by x1k. x2n has got an endpoint DFT given by x2k. Then a x1n plus b x2n will be having an endpoint DFT of a x1k plus b x2k. So you have the same linear combination for the transient domain. You have the same linear combination for the transient domain. Now, evidently, you can combine a x1n plus b x2n only if x1n and x2n are of the same length. Do you understand this? Otherwise, this is not applicable. Otherwise, this linearity property cannot be applied. Is it understood? You are looking at endpoint DFT. Say, you cannot have x1n as a 3-point sequence giving a 3-point DFT and x2n as a 5-point sequence giving a 5-point DFT. You cannot combine these two sequences in a linear manner. You cannot apply superposition theorem there. So to apply superposition theorem, it is essential that you are looking at the same endpoint DFTs in both the cases. Is that understood? Any doubts? x1n cannot be a 3-point sequence and x2n cannot be a 5-point sequence. If x1n is a 3-point sequence, x2n has to be a 3-point sequence. Otherwise, you cannot apply this property. You are looking at the same value of n throughout. If x1n is an 8-point sequence, definitely x2n also has to be an 8-point sequence for them to be linearly combined. You are not just adding. For the linearity property of the DFT, it is essential that both the sequences are to be of the same length. Is it understood? Is this understood? Or do I need to graphically illustrate this again? Anyone? See,
Yes, sir, it is understood.
Okay. This is okay. So can I move to the next slide?
Yes,
I
sir.
hope, okay. So now we look at the second property. So this is very peculiar to the DFT, discrete Fourier transform. Now you are looking at the circular shifting of a sequence. Circular shifting of a sequence, and we will also look at the corollary, which is the circular shifting of a DFT. We will see what will happen if we circularly shift. So we have a new word here, circularly shift a sequence. Do you remember in the previous year, we had looked at x of t having a Fourier transform given by x of omega, continuous. And x of t minus td, that is the signal x of t is delayed by td samples, sorry, td seconds. Then it gave you a spectrum given by e raised to minus j omega td into x of omega, which means you have an additional phase shift of omega td. Additional phase shift of omega td. So this is the corresponding property for discrete Fourier transform. Likewise, you would have seen the corresponding property for discrete time Fourier transform. If x of n had a DTFT given by x of e power j omega, then x of n minus nd is the number of samples by which the input sequence is delayed. The sequence is delayed. Then that will have a DTFT given by e raised to minus j omega nd into x of e power j omega. So this will give you an additional phase information which relates to the number of samples by which it is shifted. So you have the corresponding property here. Now, before doing anything, I want someone to, so I will pick someone at random. Afreen Amir Khan, class in Andala. Afreen Amir Khan, okay. So I want you to just read out what is written there. Just read out. Just read.
Sir, read the slide, right?
Read this slide. Only read this slide. Starting with this, if.
Circular shifting of a sequence. Circular.
You needn't read the title, but the rest you can read.
If x of n over n DFT
you just read it. If x of n has an endpoint DFT given by x of
DFT x of k, then x of n minus m modulo n,
right.
where n is between 0 and capital N minus 1.
Read 0 less than or equal to n less than or equal to n.
N less than or equal to n minus 1 over n DFT. W
has an NDFT given by
NDFT given by W n raised to nk into x of k.
Okay, so we'll stop with that.
Okay.
We'll stop with that. Now, what is x of n modulo n? Afrin, you can continue. What is x of n modulo n? We started today's class by discussing the modulo operator, right?
N modulo n is like 0, 1, 2 up to n minus 1.
N modulo n, x of n modulo n refers to periodicity of the signal. Do you remember? N modulo n is the remainder of n divided by n.
Yes.
And you have seen the case of the negative numbers as well. So x of n modulo n. So n modulo n is the
remainder of n divided
by n, and it is therefore reduced to a number between 0 to n minus 1.
N minus 1.
Okay, so therefore x of n modulo n would be a periodic sequence, right? Which we call as x tilde of n. So x tilde of n can be this periodic sequence. Okay, so what is therefore x of n minus n? Just tell me what is x of n minus n.
X of n minus n
is x of n divided by m samples, right?
Delayed by m samples.
M samples.
So shifted in the right direction.
Shift in the positive direction by m samples. So what will be x of n minus n modulo n?
It will be n minus n divided by remainder of n minus n divided by
n by n. So which means it is the periodic signal for which one period is x of n minus n modulo n, right? Is that understood?
Yes.
This is a periodic signal for which one period is x of n minus n modulo n. So that will have a DFT given by W raised to n k in the x of k. So this is what we are going to try to prove. We'll look at this illustration here. Look at this finite duration signal. Okay. This is x of n. How many samples are there in x of n? You can see how many samples are there in x of n. You can just count how many samples are there in x of n.
6 samples.
There are 6 samples. Right? So 0 to 5. Right? X of n has got samples from 0 to 5. N minus 1 is equal to 5, n is equal to 6. Now, we will form a periodic sequence x tilde of n with x of n. This is the periodic sequence x tilde of n with the x of n as one period. Okay. See, this is one period. I will repeat that here. I will repeat that here, and I will continue. So this is my periodic sequence. I will call this as x tilde of n. Now, in this example, the sequence is shifted to the left, not to the right. So n minus, instead of n minus m, here they are looking at n plus 2. Or maybe I can see m is equal to minus 2. So this will be shifted to the left hand side. So x1 tilde of n is my new periodic sequence, which is x tilde of n plus 2, which is x tilde of n shifted to the left by 2 samples. Understood? X tilde of n shifted to the left by 2 samples. And now, if I take one cycle of that, that is the period of x tilde of n plus 2. See what is happening here. We will compare this period or this signal with this signal, the first and the last signals. See what is happening here. It is shifted by 2 samples to the left in the negative direction. See what is happening here. So this sample is shifted out and placed at the end. And the last button sample is also shifted out and placed at the end. So in fact, you have a circular shift. Now what I will do is I will again go back to my whiteboard and illustrate this with some numerical value. Okay, so let me look at a numerical example here. I'll put some number so that will be easier to understand instead of drawing that. Let me look at x of m is equal to 5, 4, 6. This should become as 5, 4, 6. There are 3 samples. Or maybe I will put one more. 5, 4, 6, 2. Okay. So x of n is 5, 4, 6, 2. Let me look at a periodic sequence x tilde of n, which is equal to x of x of n modulo n. So in this case, capital N is equal to 4. So x tilde of n I can write as x of n modulo 4 will be equal to what? 5, 4, 6, 2, 5, 4, 6, 2, 5, 4, etc. So this is my periodic sequence. I'll put this as my origin. Okay. Now let me look at x of n minus 2 modulo 4. So that will be same as x tilde of n minus 2, which is equal to. So I move this sequence by 2 samples to the positive direction. So if I move this by 1 direction, this 0 will be here. If I move this by 2 samples, this 0 will be here. So what will be the new cycle now? 6, 2, 5, 4. 6, 2, like this. So this will be 6, 2, 5, 4. Right? So what we have done is we have shifted the periodic sequence by 2 samples to the right. So the origin would be now at this point. And now we will write one cycle of this. So this I will call as x1 tilde of n is equal to x of n minus 2 modulo 4, which is equal to x tilde of n minus 2. And I will take one cycle of this. How will I write this? One cycle of this. I will call this new sequence as x1n, which is equal to x of n minus 2 modulo 4 for 0 less than or equal to n less than or equal to n minus 1, which is 5 here. So, sorry, n minus 1 is what? Zero less than or equal to n less than or equal to 3. So which will be equal to what is x1 of n? This is equal to, I'll put the numerical value here, 6, 2. So here now you have the 0 here. So 6, 2, 5, 4. Any doubts? So now let me look at x of n. I will draw x of n and x1 of n now. So x of n was this sequence. 5, 4, 6, and 2. So this is 0, 1, 2, 3. This is etc. 5, 4, 6, and 2. And what will be x1 of n therefore? X1 of n, what is that? X1 of n is 6, 2, 5, and 4. This is 6, 2, 5, 4. Now, how are these two related? How are these two related? These two are related via a circular shift. Now, let us see how the circular shift is affected. So, the circular shift is affected like this. See? In this manner. So 2 initially comes to the front. If you are shifting by 1, then the sequence would be 2, 5, 4, 6. If you are circular shifting by 2, the sequence would be 6, 2, 5, 4. Is that clear? So shifting is done in the posterior direction, and the posterior direction is shown as the anti-clockwise direction. As you know, when your phaser rotates in the anti-clockwise direction, increases the angles from 0 to 90 to 180 to 270 to 360 degrees. So that is why you call the anti-clockwise or the counterclockwise direction as the positive direction of rotation. So this will be 5, 4, 6, 2. Okay, is that clear? So let me rub this off. I need the last figure, that's right. It's very cumbersome. So now we have dropped the formation of the periodic sequence, and then we can directly write out the circular shifting directly from circular shifting directly from the finite duration sequence itself. So I'll write that here. So x of n is equal to 5, 4, 6, 2. There are 4 samples, 5, 4, 6, 2. And now I am going to look at the sequence x of n minus 1 modulo 4 for 0 less than or equal to n less than or equal to 3 is given by, what will be that value? Meenakshi or Anthony, whoever can answer this, anyone can answer this.
Sir, it will be like 2, 5, 4,
Right,
6.
right, exactly. This will be 2, 5, 4, 6. Very good. So what will be x of n minus 2 modulo 4? If I write this, what will be the value? Meenakshi, what is this?
This will be 6, 2, 5, 4.
No. It's not a finite duration sequence, it's a periodic sequence.
Oh, okay, sir.
Okay,
That
so,
n limit was
so
not given.
I have not written that 0 less than or equal to n less than or equal to n minus 1. So that would be, if I have to write this as 0 less than or equal to n less than or equal to 3 is equal to 6, 2, 5, 4. So this is my positive direction of rotation, 6, 2, 5, 4. I have moved in the positive direction, so it's rotated in the counterclockwise direction. I will always put this curve upwards in the top of the lines, in the top part. like this. I will not put the lines here. I'll not put the rotation of the phasor or rotation of the sequence below the line, below the x-axis. I'll always put this above this angle. So suppose I require x of n plus 1 modulo 4. What is x of n plus 1 modulo 4? Now tell me what is x of n plus 1 modulo 4? N plus 1 modulo 4 would be?
When the limits are applied,
So I will put the limits also. I'm looking at a finite version, 0 less than equal to n less than equal to. What is that? What will be that?
4, 6,
4, 6,
2, 5.
That is 4, 6, 2, 5. So what we have here is now a rotation in the clockwise direction. This is the negative direction. So 5 will go here. 5 will go towards him. So likewise, x of n plus 2 modulo 4 for 0 less than n less than equal to 3 would be, what is that value? What will be that?
That will be 6, 4, 2, 5.
That will be 6, 4,
2, 5.
okay. That's how you will compute the values, right? 6254. That will be sorry.
4, 2.
This is now 4625. So again, this 4 will come towards the end. Okay. So in this case, you have similar values. Anyhow, you will understand that the rotation is in the positive direction when you shift in the rotation is in the positive, that is in the clockwise and counterclockwise direction if you shift in the positive direction, and the rotation is in the clockwise direction if you shift in the negative direction. Okay. Now we will prove this property now. So the proof is fairly straightforward. How will you prove this? We look at the corresponding property for the discrete Fourier series. So if we have this Fourier series x tilde of n having a Fourier series given by x tilde of k, you are required to find out what is the Fourier series for x tilde of n minus m, for which we will write down the analysis equation. So the analysis equation states that sigma n equal to 0 to n minus 1 x tilde of n minus m Wn raised to nk, right? Wn raised to nk. So this is a summation over a period. So I can take any period. So that will not make any difference to my summation. I can take n equal to 1 to n, n is equal to 2 to n plus 1, n is equal to n minus 1 to 0. Doesn't make any difference. And or n to 1, etc. Any value. So you only need to sum over one period. So this is very easily proven by, let us put n minus m is equal to p. So, and then we'll write n is equal to p plus m and write this as summation over some period, but the summation over p. So this will be x tilde of p into Wn raised to, instead of n, I will write pk into Wn raised to mk. So here m is my constant. M is the amount by which I have shifted the sequence. So p is my new variable. So this will be summation over when n is equal to 0. When n is equal to 0, then p is equal to minus n, right? And when n is equal to n minus 1, n is equal to n minus 1. Why? Is that clear? When n is equal to 0, p is equal to minus n. When n is equal to n minus n, p is equal to n minus 1 minus n. So this is summation over one period. I can do the summation over any period, so that will give you the same summation. So this is also therefore equal to sigma over p equal to 0 to n minus 1 x tilde of p into Wn raised to pk, and I can take this Wn raised to mk outside. Is it understood? Wn raised to pk, sigma of p equals 0 to n minus 1, actually of p, Wn raised to pk outside. Then I will take 1 period for this. If I take 1 period, I will continue somewhere here. Okay. So 1 period, x tilde of n minus m. So sorry, from this x tilde of x of n minus m modulo n. I will take 1 period of that, so I will have to write therefore 0 less than or equal to n less than or equal to n minus 1. We'll have a DFT. So I'm going to take the DFT therefore. We'll have a DFT given by Wn raised to mk, and see, this is sigma p equal to 0 to n minus 1 x tilde of p, Wn raised to pk. So this will be a function of only k because you are summing your p. So p, n, etc. are variables that vanish in this summation. So I can even replace p by n. So n equal to 0 to n minus 1 x tilde of n, Wn raised to mk. So this is in fact your x tilde of k. So this is x of k. Sorry, x of k. So clear? This expression is x of k because you are only looking at 0 less than or equal to n less than or equal to n minus 1. Is it understood?
Yes, sir.
Okay. So now we have proved the property, circular shifting property of discrete Fourier transformation. In fact, the properties are very straightforward. So after a while, it will become very tedious and it will be very boring for you also. So I think it will be better if we can prove a few of the properties by yourself. I will again go back to my PowerPoint presentation. I will finish this property and then we will take a break. We'll take a break of 15 minutes and then we will continue. Okay, so let us go back to the presentation. Okay, so this is how the circular shifting was illustrated. Okay, now we will need the circular shifting to deal with a very important, in fact, the most important property of discrete Fourier transforms, which is known as the circular convolution property. Okay, the circular shifting property is read like this. If x of n has got a, now, Afrin American, Afrin.
Yes, sir. Yes, sir.
Now you can read the other part of it. First part, you can start with this, and you can start with the if x of n has got an endpoint DFT given by x. Okay, you can start like that. Please start.
If x of n has got n DFT,
Endpoint DFT. You read this as endpoint DFT.
Endpoint DFT given x of k, then x of n minus n modulo n was 0 less than or equal to n less than or equal to n minus 1 for n point DFT given Wn raised to nk into x of k.
This is what we have proved now. This is what we have proved now. What we have proved is this one. Okay. Okay. Now read the other one. Read the other one.
Wn raised to minus nl x of n for n point DFT given x of k minus l modulo n was 0 less than or equal to k less than or equal to n minus 1.
Okay, so can you prove the second part? Can you prove the second equation? Now, before proving the second equation, I want any one of you to explain what is the second equation. You can make a guess and tell me. Arvind Palat class lunda. Arvind Palat is there. You are there in the class, right?
Yes, sir.
Arvind, look at the second equation and tell me what is happening in the second equation.
It's actually the inverse of the previous
Ah,
property.
it's in fact, you do not call it as an inverse, you call it as a dual.
Opposite. Okay.
You call this as a dual of the previous equation. So what is happening there? Can you explain that?
When the sequence is multiplied by
Let us
an
start
e
with what
raised
is
to
happening on the right hand side. We look at what is happening on the right hand side, and then we'll go to what is happening on the left hand side. So let us look at x of k minus L modulo n, 0 less than k less than equal to n minus 1. See what is happening there. You are circularly shifting the discrete spectrum, right?
Yes, sir.
All right. So when you circularly shift the discrete spectrum, when the discrete spectrum is circularly shifted, what is happening now on the left hand side?
The sequence will be multiplied by
By what? By Wn raised to minus L. What is that? Wn raised to minus L is the complex exponential e raised to minus j to pi by n, e raised to minus j to pi by n, the whole raised to minus n.
minus nl.
So that is e raised to j to pi by n into nl. So this is in fact a kind of a modulation, right? You are
Yes.
modulating x of n by a complex exponential. So you are shifting in the frequency domain. The equivalent property for the discrete time Fourier transform was x of e power j omega minus omega d. You are shifting in the frequency domain. What will happen? The time domain is multiplication of the signal x of n by a complex exponential. So instead of that shifting, which is a linear shifting in the frequency domain, now you have a circular shifting in the frequency domain. Wherever you find linear for DTFT, you have a circular shifting as far as this shifting of the signal is concerned. So x of k minus L modulo n, 0 less than k less than n minus 1, is a circular shifting in the positive direction of the discrete spectrum x of k by L samples. Circular shifting by L samples in the positive direction. This will result in a multiplication of the sequence x of n by a complex exponential. And now what is that complex exponential? Wn raised to minus nl, which is e raised to j 2 pi by n into nl. Is that clear? So it's somewhat like a modulation. So now what we'll do